Part A, complete the table below with the expected frequencies on the assumption that each day should be equally proportioned to the calls received. So in this Austin Police Department, they received 147 calls during a week. Now, if they were evenly proportioned, which they aren't in this table here, which is the actual values, but if they were evenly proportioned, then they should have an even amount on the 7 days of the week here. So that's the purpose of this question. Part A is to have a expected value for even proportions. And looking at the solution here, what we need to do is to divide the total number of calls, 147, by 7, or another way to think about that is to multiply it by 1 on 7. So we get an answer of 21 here. So on each of the 7 days, if the days were evenly proportional or evenly spread, there should be 21 calls on each day. 21, if you add these all up, that'll add up to 147. So that right there is our answer to part A. Part B has 3 parts, and in these 3 parts, we are working through a chi-squared goodness of fit test. Okay, so we are told that a chi-squared goodness of fit test is performed at a 5% significance level. So what this means is this chi-squared goodness of fit test, it's a measure of the population proportion of a sample of data. So what I mean by that in the context of this question is 147 calls were studied in a sample of calls over a given week from this police department here. And we can see here that the number varies throughout the week. So for example, Tuesday didn't have many calls compared to Wednesday. Wednesday and Thursday, there was a lot of calls. So potentially more calls are received on Wednesday and Thursday. Now we're going to compare that against the expected number of calls. And we are told that the police department expects the number of calls to be evenly distributed throughout the week, which is what we found in part A. In this table in part A, we determined that if it is evenly proportioned, the number of calls should be 21 calls per day. So a chi-squared goodness of fit test allows us to determine these discrepancies in the observed values, these ones here, was that just randomly by chance? Or is there actually an underlying reason for a difference? And we're going to prove whether it's statistically significant to say, no, the calls are not evenly distributed. And that'll allow the police department to maybe put more staff on say, a Wednesday and a Thursday, and maybe less staff on the Tuesday. So there's good reasons to be performing these tests. Okay, let's start with the first part of part B, which is to state the null and alternate hypotheses. Well, the null hypothesis for a chi-squared goodness of fit test is that, in this case here, the calls are evenly proportioned. So we set the scene here and say, okay, the null hypothesis is that the calls are evenly proportioned over all 7 days of the week. It's always the even probability. So, for example, flipping a coin 100 times, your null hypothesis is that we should get 50 heads and 50 tails, and then we need to prove that wrong. The alternate hypothesis is that they are not evenly proportioned over the 7 days of the week. Okay, the second part of B asks to write down the number of degrees of freedom. Pretty easy, this one here. The number of degrees of freedom is the number of categories, in this case here, number of days of the week. For flipping a coin, it would be heads or tails, that'd be 2. It's the number of categories, subtract 1. So in this case here, our number of degrees of freedom is 6. Now you may be wondering why we bother calculating this. Well, we don't actually use this any further in this question here, but it is actually quite useful to determine the critical value. But we are actually given the critical value in part C. But if we didn't, if we weren't given it, we could actually use a critical value table here, which is this one you can see on the top right, and say, okay, I have 6 degrees of freedom. I'm going to perform the chi-squared goodness of fit test at a 5% significance level. So therefore my critical value is 12.592. So you just read it off that table there. So that's the purpose of that. Okay, let's now get into the crux of the question here, which is to use our calculator to find the chi-square statistic and the p-value. Let's go ahead and find that, and then I'll explain what the two numbers mean. Okay, so we're going to be entering data into our spreadsheet. So let's open up the statistics section. We're going to create 2 columns. The first column is the observed value, so I'll title that O. The second column is the expected value, so I'll title that E. So let's go ahead now and enter the data. So the observed values are the actual calls received in the sample. So it's 22, 18. I'll just pause the video and finish this. Okay, that's the first column completed, the observed column. Let's now go to the expected. The expected will be the table that we completed in part A. We expect that there should be 21 calls each day. So 21, 21, and again, I'll pause the video. Okay, that's the data entered there. Let's now go ahead and perform a chi-squared goodness of fit test. So we go to the top of the next available column. Let's go menu, number 4, statistics, number 4, stat tests, and we're going to choose number 7 here, chi-squared goodness of fit test. So the observed list is the column that we labeled O for observed. The expected list is the column that we labeled E. The degrees of freedom, we found that in the previous part, which is 6. And we hit OK, and here we get our value. So our chi-squared statistic is 2.95, and our p-value is 0.815. Well, I have a little error there, I'll fix that up, but rounded to 3 significant figures is 0.815. Okay, let's just talk briefly about what these two numbers mean. If I have a look at my chi-squared distribution here, and I think it's always good to visualize this distribution because then these two numbers start to make sense as opposed to just trying to remember what to do with them. So in this chi-squared distribution here, I have my chi-squared values on the horizontal axis from 0 and getting larger. A chi-squared value of 0 would mean that there is no difference between the observed values and the expected values. And in this question here, that would mean that the number of calls in the sample would just be 21 on every day. So our chi-squared value would actually be right here at the origin would be 0. But the larger the difference between the observed values and the expected values, the further to the right this chi-squared value gets. Now, wherever this chi-squared value is, and let's say it's at this point here, which we call the critical value, the area under the curve to the right of that is the probability that that chi-squared value can occur by chance, given that the null hypothesis is true. So obviously, the further to the right this the probability gets lower and lower and lower, all the way to the point that we have potentially 1%. There's a 1% chance that the chi-squared value could occur given that the null hypothesis, which is that the calls are evenly distributed, is true. So in other words, if you want to simplify that down, think, okay, the bigger the chi-squared value, the less probability that the null hypothesis is valid. Now the p-value, the probability value, in this case here we have 0.815, so this is 81.5%. I like to think of this as a percentage, and what this means is there's an 81.5% chance that the difference between the actual values, which is these values here in our table, and the expected values, these ones here, there's an 81.5% chance that the difference just occurred by chance, and there's not actually a true underlying reason for that difference. And that's a pretty high percentage. So there's an 81% chance that this just happened by chance. So therefore I'm thinking, well, there's no real reason for me to disregard the null hypothesis that the calls are evenly distributed. But we're going to get to that in part C. But this probability value here, the 81.5% or 0.815 as a decimal, that's the area under the curve to the right of our chi-squared value. But we'll talk about that more in the next part, part C. Part C, we are told that the critical value for this test is 12.592, and we are to determine the conclusion for this test, providing a reason. Okay, so just to recap, in this question here, we're performing a chi-squared goodness of fit test, which is comparing the actual results of a sample with some expected values, and then determining whether the proportion of the expected is the differences in the proportion, whether they are just by chance or whether there's actually a reason for it. And in this case here, we have the number of phone calls. We can see that they are slightly higher on Wednesday and Thursday. We want to understand whether, is that just a random occurrence in this sample of this week? Or actually, are there more calls on Wednesdays and Thursdays? And therefore, can we maybe put more staff on Wednesday and Thursdays and maybe less staff on Tuesdays and Fridays and Mondays as an example? Now in part B, in the third part of part B, we found the chi-squared value of 2.95 and the p-value of 0.815. Now, we are given the critical value of 12.592, and if I go across to my chi-squared distribution, I think it's very important to think about it in a visual sense. And once you understand that, this comparison actually becomes quite easy to do. So in this chi-squared distribution here, we have our chi-squared values across the horizontal axis, starting at 0 and getting larger. If the chi-squared value is 0, that would mean that there is no difference between the expected values and the observed values. Now, the larger the chi-squared value gets, the smaller the probability that the expected results were achieved by random, by chance, and therefore the stronger the argument to reject the null hypothesis that the number of phone calls per day are evenly distributed. So in this case here, our critical value is 12.592. So that's this point here on the chi-squared distribution. That's this point right here. See how it says chi-squared CV, 12.592. Now, if the chi-squared value was to be greater than the critical value, then we would reject the null hypothesis because the probability of the expected results occurring by random would be too small. In our case, though, we have a chi-squared value of 2.95. So that's about here. That's really low. So therefore, the probability of the results occurring by chance is actually quite a lot. All the area under this curve here. And we actually do know what this area is because it's our p-value, 0.815. In other words, there's an 81.5% chance that the expected results that we got in the survey did happen by chance, and therefore that we won't reject the null hypothesis. So we could use either here. We could use a comparison of our chi-squared value to the critical value, or we could also use a comparison of the p-value, the probability value of 0.815, in comparison to the significance level. This is this 5% here. And just to connect the dots here, at the critical value, 12.592, the area under the curve to the right of that is 5%, the significance level, or as a decimal, 0.05. Okay, so in conclusion, because the chi-squared value is a lot lower than the critical value, we can say that we will not reject the null hypothesis. Hence, there is insufficient evidence to conclude that the calls are not evenly proportioned over the 7 days. So, although there is a variance in this sample, it is not statistically significant, so therefore the police department shouldn't start changing their staffing. They shouldn't start putting more people on Wednesday and Thursdays and less people on Tuesdays and Mondays, because the next week it might be random in a different way. We might have more calls on Monday and Tuesday and less on Wednesday and Thursday. It was completely random. Okay, so that is the answer to part C.